what are called infinite series. So far, everything we've done has been a finite series, whether it's arithmetic or geometric, and it makes sense, right? I mean, if I have a series that looks like this is an arithmetic series. What's the point in looking at an infinite series? A finite series is okay, series to 10, because that's going to be some bigger number, and series to 20 is going to be an even bigger number, and series to 50 is going to be an even bigger number. But doing like a sum to infinity, that's it. It's infinite. You know, whether it's 3 plus 5 plus 7 or 21 plus 49 plus 77, you know, it doesn't matter what the size of the number is to start or the gap between the numbers. Ultimately, yes, an infinite series. So it goes to infinity. Boring. Trivial. Or negative infinity, of course. If I started off with s to infinity of, say, -3, -5, -7, minus, okay, that's just going to go to negative infinity, which is slightly more interesting because it's got an extra little character in it, but is really trivial as well, right? So it's boring. Now, geometric series, on the other hand, so much more interesting. So if I go sum to infinity of 2 plus 4 plus 8 plus 16 plus, that's so much more interesting, isn't it? So much more. No, it just goes to infinity as well. It's actually pretty boring. But the exciting thing is, because it's exponential, it gets to infinity much faster. No, of course not. Infinity is a concept, right? It's not a thing. It's a concept. It's true that the series increases at a faster rate, but you can't. Infinity is weird. You can't talk about it quite in those terms. So the point is that there's only a single case where looking at a series to infinity makes sense. Now, what I have is a couple of graphs here to sort of demonstrate what I'm trying to say, generally speaking. So here we have an infinite geometric series, but what I've done, the graph does not represent a sequence, right, like we've done in the past. Each of the points on that graph represents a sum to a certain number of terms, okay? So at the moment, this is going to be hard for me to capture in the video, right? But at the moment, I've got a equals 2 and r equals 1.03. So the general term, u sub n, is going to be 2 multiplied by 1.03 to the power of n minus 1. That's the sequence. The series is the sum of that. Okay, so S1 Blop, 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 blop. Bloop. So S1 is the sum to one term. That's that there. The sum to one term is 2. Unsurprising, it's the first term. The sum to two terms is that one there. Oops. 4.06. Okay. The sum to three terms would be this one. So this line here, this very steep line, isn't a. It's a mapping of all the different series. And as you can see, as I go up, S1, S2, S3, S10, S50, S100. Sorry, I'll get rid of that board now out of the way. As I go up, boringly, it just means, in terms of the picture of the stuff, boringly, all that's really happening is that the value of the series is getting bigger and bigger and bigger. Boring, okay? And that's the nature of it. As I increase R, all that's happening is that it's, like I said before, a really bad way of saying it, but it's getting to infinity faster. As I decrease it, or if I go negative, it's the same deal. Oh, I can't go negative because I haven't got it there. So if I go negative, it's the same deal, but oh no, that's right, the graph. That's why I didn't do it, because graphs don't work with negative numbers, remember? You probably did, I didn't. Anyway, so we got this idea that it's just growing faster and faster as I increase R, but it's basically a sum to infinity. The sum to infinity is infinity. Boring, 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 boring. So the interesting part of a sum is where we have a look at R being a fraction. Okay. Oh, by the way, it's not that hard to create a sum to infinity that actually is slightly more interesting, but still pretty trivial. And it doesn't require geometric series or arithmetic series or anything. If I just go the sum to infinity of -1 + 1 - 1 + 1 - 1 + 1, what's the sum to infinity there? Is it? Is it though? Depends on which infinity I finish on, is that what you're saying?
But if the last term in the sequence is...
It's the sum to infinity. Hang on, again, the video will miss this, but you know what I mean? Like, it's not actually, I don't have an answer for you. And the answer is, I think the answer is something like, it's something really weird. I can't remember, like 16 or something. No, it's a fraction, 23/5 or something like that. Yeah, I'll find the number file video for you, but it's not a trivial answer because Arit said 0, didn't you? Lily said depends on where you stopped, which I'd say 0 and why. It's only 0 if we assume infinity is even.
Yeah.
If infinity is odd, it's going to be -1. But that doesn't really make sense because infinity is neither even nor odd.
Can you say, like, if the number of terms is pair, it will be
maybe one or the other. But that almost implies, though, that you're picking an endpoint. And as soon as you're picking an endpoint, it's not like if I said to you, what's the sum of the sum to infinity of that series there to 1,000,000,001 terms, the answer is -1. If I say, what's the sum to 50 billion, the answer is 0. You know, infinity is beyond that, beyond the concept of even just, infinity is not a large number. Infinity is beyond that. Infinity implies there is no stop. There is no stop. Not just it's way so far out we can't see it. There's no stop. This is why mathematics is way cooler than physics. Because in physics, there's always some sort of physical limitation, right? Whereas in mathematics, we say 8 dimensions or 18 dimensions if you're a cosmologist. I think we can go a bit further than that, and we go to infinity, right? So that's why mathematicians are way cooler than physicists. See, no, because infinity, again, it's just a concept, I suppose, but it implies something extraordinarily large, and it's definitely not extraordinarily large. I'll find the number file video so you can have a look at it. But it's tricky, isn't it? It is tricky concept. And infinity does this to your brain. If you want to do an extended essay around the concept of infinity, such a cool extended essay to do, I reckon. Because you can do it for your IA, you can do it for extended essay as well. It's a really interesting sort of thing to sort of, it's a theory of knowledge almost, isn't it, really? What is infinity? What does it mean? Because it's tricky. Infinity says this. You know how 0.99 is approximately equal to 1? It is, isn't it? It's approximately equal to 1. So is this. That's really, really close to 1. It's even closer to 1 than what I had before. Infinity, which is putting 3 simple dots at the end, says that is exactly equal to 1. Not approximately equal to 1, but it's exactly equal to 1. And to answer, we're going to have a look at this in this next part of the unit, but to a really simple way of looking at it is, if it's not equal to 1, then there must be a number between it and 1. What is that number? It doesn't exist. Nothing exists between 0.99 recurring and 1. Nothing exists. There's no number. Any other 2 numbers you can choose, there's always something in between. Between 0.01 and 0.001, there's an infinite number of numbers between those two. But between 0.9 recurring and 1, There are no numbers between them. Therefore, they're the same. There is no difference between the two. They are literally the same. William?
Is there a notation to say that the number after the point is infinite?
Yeah.
To say like exactly
like that?
value of one.
I don't know whether you've used that notation yourself. I'm not too sure if it's universal or not, but the dot over the digit means that digit repeats forever. Yeah. If it's a sequence of digits like 1, 2, 3, we put a bar over it. Sometimes you'll see it written, I don't like this, as a dot at the start and a dot at the end and say that's the repeating digits. Yeah. Okay, anyway, so that is exactly a good one. 0.9 recurring is how we would say it, is exactly equal to 1.
Does that mean that like 1.9
recurring exactly equal to 2. Yeah. And the simple way of thinking about it is because there's no number between them, therefore they must be the same. But in this unit, we're going to have a look at something a little bit more not mathematical, it's all mathematical, a little bit more calculatable to get to the same result. But anyway, that's down the line a bit. So the interesting spot then. So it is possible to come up with interesting sequences, regardless of whether they're arithmetic or geometric, that go to infinity, that have interesting properties. But specifically, we're going to have a look at geometric sequences because they have some specific things which are quite interesting to look at. Again, I'm going to look at the positive numbers because I can't graph the negative R, but it works for negative R as well, what I'm talking about. It's just that it alternates. So I'm going to bring R down to 1, which is tedious, but then I'm going to go down to a fraction like I'll go down all the way down to 0.5. Have a look at that, or 0.6, that'll do. Have a look at it now. The sums, yeah, it's an asymptote. Thanks, Zoe. It does look like an asymptote, doesn't it? The sum, the series, as I approach infinity, as I get bigger and bigger numbers, so the sum to 10, the sum to 50, the sum to 100, I'm actually not gaining much in my sum. I'm not gaining much in my sum, okay? Which means that there's a theoretical limit that the sum is approaching. So you can see the sum to 2 is here. It says undefined, but we know it's just 2. And then as I'm going up here, the sum is approaching 4, 4.4, 4.5, 4.6, 4.789, 4.932. It's definitely still growing, but it's growing smaller and smaller. So the jump between the sum of one term and the sum of two terms is quite big, isn't it? It's a big jump there. But then if I'm looking at the sum between the sum of 6 and the sum of 10 terms, it's a really small jump in what the total sum is. And then if I zoom out, you can't, visually, it's not, but it looks flat, which is why Zoe said something about an asymptote, okay, which is a theoretical hard limit, okay, so that we've got a specific value that the sum will approach and never get to, kind of.
Does it matter that in the brackets where you put in the function that x is greater than 1? Or you've just put that in to show us?
Just to show you, yeah. It's just to cut it off because we know when x is equal to -1, it does weird things. Yep. No, sorry, that's not the right reason. The reason why I've made x greater than 1 because in this function here, x takes on the value of n. And in a series formula, it's u1, which is a, outside of 1 minus r to the power of n, all over 1 minus r. I should have explained that, and I forgot to. You can see that my function here is just the series formula. Y is s, a is u1, and x takes on n, which is why I've got x bigger than or equal to 1, or bigger than 1, because at 1 it's actually not defined for a function. Is that okay? Everyone okay with that? Okay, so it has this property that when r is a fraction, it seems to flatten out. So what we're seeing here are two special words. I don't think you need to know them, but it's useful to just see them. As soon as I get above 1, it's curving this way now instead of curving that way. We call this, when R is bigger than 1, a divergent series. As the series increases, as the number of things we're adding increases, so does the series, and so it diverges. All arithmetic series are divergent, and geometric series are divergent if R is greater than 1. But if we have R less than 1, then the series converges to a limit. It converges. It's a convergent sequence, to be more precise, or a convergent series. It converges to a value. Divergent means it just goes to infinity. Convergent means it goes to a value. Okay. Since Zoe mentioned, I was going to do something else in between, but since Zoe mentioned it though, this video here just puts in that, this graph puts in the asymptote. And have a look at how the asymptote is the purple line. You can see here is the asymptote here. Just give you a moment to think about why this formula gives me the asymptote. So I'll zoom out a little bit, and you can see that as R is less than 1, you can see what that convergent value is. Sorry, is getting closer to 0. If I go to a half, it's probably going to be a little bit tidier to see the value. Y equals 6. And then as I go towards 1, we can see that series is changing here as well. Okay. But the purple line is effectively the hard limit for that series. And we say that the series converges to that value. Okay, so at 0.7, the series converges to 10, for example. And the asymptote gives us. Why? It looks similar, doesn't it? Look at my asymptote. So good we've done exponential functions, because you don't normally talk about asymptotes when you're doing geometric series, but it's really good that we can visualize it, I think, because we've got the language for it. So it looks similar, I think. Does it not? What's the difference between the two, and why does that make a difference? That's the bit that's missing. Good. Why does getting rid of the 1 minus r to the x give us the asymptote, the value to which the series is converging?
The power is the part that makes the curve.
Say that again.
The power is the part that makes the graph curve.
Yeah, cool. So I want to tease it out a little bit. You're right, it's to do with the power and to do with the value of r. But I could go y equals a, and that would also give me a straight line, but it doesn't give me the asymptote at all. It just gives me a straight line. So why is it that specifically the getting rid of the 1 minus r to the power of x bit doesn't just give me a straight line because we've got rid of the power bit, but it gives me, you can see the straight line changes, and it is exactly the asymptote for whatever that function is here. This function here has an asymptote here. Let's remember what an asymptote is. It's the limit of the function as x approaches infinity. So it's the upper, people can't see me doing this on the video, but I'm holding my arm up. It's the upper limit, which in this case, the series, the function goes towards but never crosses, but it reaches towards it. Okay, so it's a ceiling for the series. It's a ceiling as x approaches infinity. Clearly, the difference between here and the ceiling is quite, I mean, this is ground floor, isn't it? Up here, we're nearly at the penthouse. All the way along here, we're pretty much just the elevator's nearly there, etc. Okay, so as x approaches infinity, the series approaches the purple line. Why? Good, I've stumped you. Have a think about it. Talk to the person next to you or opposite you or whatever else. Zoe and Lily, talk to Siggy. Any thoughts?
Still nothing
Mull away.
the last point, you know?
Yeah.
It's the same. Like,
What you thinking?
it's the same that if you have a distance,
Mm-hmm.
each time you do half of this
Mhm.
distance, you will never arrive at the end, just be closer and closer.
Have you heard of the frog hopping towards a wall? That kind of thing. So if a frog is 10 meters away,
Yeah.
and it hops half the distance each time it hops, when will it reach the wall?
Never.
Yeah.
Yeah.
So the distance of the hop gets smaller and smaller.
Yes.
So there is definitely something in that.
It's a Greek myth, isn't it?
Is it?
Yeah,
Is it really?
I think so. It's about a guy who could, there was a human runner and a god runner, and he could run half the distance in each stride. He never made it to the finish line.
Oh, I didn't know that's where it came from.
Yeah.
Yeah,
So I remember
interesting.
hearing another guy saying, you know, if you had a minute,
Yeah.
turn the light on and off, you're reaching infinite finite time.
Interesting. I haven't heard that one. Okay. Do we have any thoughts that you'd like to share? Okay, it's got to do with R, doesn't it? Because R is a fraction. Okay. Yeah, pretty much. If I have I'll just switch over to Air Sketch for a second. And William, you were saying it's down the back. That as you continue to go to a bigger and bigger series, that fraction is getting smaller and smaller and smaller and smaller. So basically, you've got a fraction raised to a positive power, I should just say. If it was a negative power, then we'd be in all sorts of trouble. But because you've got a fraction raised to a positive power, as this positive power approaches infinity, we're basically going to have fraction multiplied by fraction multiplied by fraction infinity times. And so we've got a fraction of 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 a so effectively it's one of those things where it's the same thing as 0.9 recurring. If I'm going to infinity and I'm multiplying a fraction by itself, effectively the result of that is going to be no different from zero. So it's zero. If you stop at the 5 billionth term, it won't be zero. It'll be very close to zero, but it won't be. But we never stop. We're continuously multiplying, getting a fraction of a fraction of a fraction. Therefore, at infinity, there is no gap between it and zero. So therefore, it's effectively zero. So what does that mean? It means that if we have a look at the infinite geometric sequence, then this bit here at infinity, which is a really loose way of saying as it approaches infinity, at infinity, this is zero. And 1 minus 0 is 1. I'm worried that no one actually called that out then. 1 minus 0 is 1. 1 times A is A? A? Yeah, A. Okay? So in other words, this has to be the asymptote. It is the limit of the series because this bit is going to reduce down to 0 at infinity. Okay? So what that gives rise to is that for an infinite series, I'll be more precise, for an infinite geometric series, we have a new formula. And the infinite geometric series is just that. Okay? At infinity, we will have a specific value, and that value will be the first term over 1 minus the common ratio. Okay, so all of that, I could have just given you the formula and said do it, but I think it's really important for you to understand and link the ideas between exponential functions, asymptotes, and why this works out this way. So infinite series. No, got to be more precise. Infinite geometric series. I'll change to black just because it's a bit easier to read. When R is a fraction, remember that's what that means. It could be a positive fraction or a negative fraction, but R has to be a fraction. Okay, an infinite geometric series is when R is a fraction. If R is not a fraction, then the answer is just infinity, so it's trivial. So the formula otherwise is the sum to infinity is equal to U sub 1 over 1 minus R. Note that I don't bother with R minus 1 because that wouldn't work. It would be negative U1 over R minus 1, which would be a silly way of writing it. Okay, so the sum to infinity is specifically U sub 1 over 1 minus R. What I'm going to do now is very briefly go through a couple of examples, and we'll go from there. But I'll just show you in practice. No, I'll just do the example, and then I'll show you on Desmos. So if I look at this series here, let's just say I want to work out the sum to infinity of 3 plus 3 on 2 plus 3 on 4 plus 3 on 8 plus and so on. Okay, so what's the first term? Call it out. Yeah. What's R? You can do it without doing many calculations, I think.
2.
Not quite a half. 2, yeah, 2 would give me 3, 6, 12, wouldn't it? So you've got to be careful because you never divide, you always multiply. Yeah, so we're halving each time. Okay, so therefore the sum to infinity is equal to 3 all outside of 1 minus a half, which is 3 over a half. And I don't know if you can remember or not, but what we do then is instead of dividing by a half, we multiply by 2 over 1. Thanks, Aaron. Spoilers. 3 times 2, which is equal to 6. Okay, so that whole thing, 3 plus 3 halves plus 3 quarters plus 3 eighths, it comes down to being equal to simply 6. And again, for the same reason I told you about 9.999999, it's not approximately equal to 6, it's exactly equal to 6. And if I go, I'm going to switch screens just for a second, guys. If you're writing this stuff down, don't worry. I'll be back in a sec. If I have a look at this, and I set R equal to 5 here and A equal to a half, you will see that you've got Y equals 6, and that is demonstrated by looking at the series here, which is clearly converging towards 6. It's converging to 6. And remember that there's always a gap between the line. Always, as soon as you stop, there will be a gap between the line. Even there, I don't know if I can get there, it's probably not. Oh yeah. Between there and there is a gap. Always a gap when you stop, but when you take it to infinity, then our brains start bending a bit, and we can't. There's no gap between 6 and the graph at infinity. Okay, at infinity, there's no gap, and therefore the series is exactly equal to 6, not approximately equal to 6. Okay, back to the thing so you can see it. Example, I'm going to do this on the fly, right? So just forgive me. I'm doing this on the fly, so it should work, but forgive me if it doesn't. Example 2. Let's do it. Let's do 0.99999 and so on. So that's an infinite decimal, right? But it could be written as a sum. Just looking at place value. Really hope this works. Okay, so U sub 1 would be 0.9. R is going to be 0.09 over 0.9. And what's that equal to? Sorry? A tenth? Yeah, or 0.1, just to keep it all decimally. Yep. Okay. The sum to infinity is going to be U sub 1 over 1 minus R. You're working ahead again, aren't you? That's going to be 0.9 over 0.9, which equals 1. Okay? So using our understanding of asymptotes, using a formula like the sum to infinity, we can show that 0.9 recurring is not approximately equal to 1, but is exactly equal to 1, because the formula tells us so. So as long as you believe in the formula, then the result follows. Okay? One last example, and yeah, and then I'll give you some practice time. I'll put these notes up on Google Classroom, so if you're falling behind, the notes will be there plus the video if you want to go back and have your mind broken again by infinity. So example 3, this is along a similar sort of line here. So I'm going to have sum to infinity of 0.3 plus 0.03 plus 0.003 plus etc. Okay, so U sub 1 is equal to 0.3. R is equal to 0.03 over 0.3, which is just 0.1. Therefore, the sum to infinity is equal to 0.3 over 1 minus 0.1, which is equal to 0.3 over 0.9. Now, if I multiply top and bottom by 10, which is just an equivalent fraction, I get 3/9, which is equal to 1/3, which PS is equal to 0.3 recurring. So 0.3 recurring is exactly equal to 1/3, not approximately. And you know that. You've seen that. That's like a grade 7 concept when you learn how to divide fractions into decimals. But it's confirmed all the way up to grade 11. It is confirmed as the result of a geometric series. Don't tend to do geometric series in grade 7. I don't know why. I do know why. But yeah, it's mathematics is wonderful like that. You know, complex results can confirm simple results and vice versa sometimes. Yep.
So in terms of writing down the answer for that, can we either write 0.3 recurring as the exact or a third as the exact?
Yes. Yep, both would be considered to be accurate. I did this to go, wow, isn't it amazing how it's all the same? That's as far as you'd need to go. My point really is that this bit here, this sum here, is 0.3333333. If you did it as a column add or something like that, that sum there is that, and confirms that both of these things are 1/3. Yep. Okay, so what you're going to do is some practice work on this. Exercise 1J. And that is on page 33. I haven't sort of separated it out to easier or harder work because I think it's all worth doing, I think. But feel free to sort of, I don't think the exercise is that big, but feel free to skip a few if you think that the early ones are more straightforward.